Let's start our lecture. So I am sharing my screen here.
Okay, sir.
So simply, so now first we are discussing what is the electrical charges and electrical forces. So you are very much familiar that there are two types of charges. One is the negative charge and the other is the positive charge. And the electric field of these charges is defined as the space or region around which the influence of the charge can be felt is known as the electric field region. Simply, for the positive charge in the convention, the arrow of the positive charge which shows the electric field is in the outward direction, while if the electric field is due to the negative charge, its direction is shown by the inward vector. So the electric field due to positive is in the outward direction, and the electric field due to the inward is in the inward direction. So now here, according to the Coulombs law, the force between two charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. And you know that the force F is equal to Q1, Q2 upon R square here. This Q1 and Q2 is the magnitude of the charges and R is the distance between them. So this is equal, the force depends upon the magnitude of charges and distance between them. If the distance increases, the force decreases. If the magnitude of the charge increases, the force increases. So now here, the Q1 charge exerts force on the charge Q2. Similarly, the Q2 charge exerts force on the Q1. The magnitude of the charge does not depend upon which charge exerts force on which charge. It means if the Q1 exerts force on the Q2 charge is the same way the Q2 exerts the force on the Q1. The magnitude is the same because the magnitude of the force does not depends upon the magnitude of the individual charges. It depends upon the product of the both charges. So if we take Q1 into Q2 will be the same as the Q1 into Q2 into Q1. So the magnitude of the force in both cases will be the same here. This K is the constant, which is the force constant, which is equal to 1 upon 4 pi epsilon naught, and epsilon naught is the permittivity of the free space. In SI units, its value is 8.85 into 10 raised to power minus 12 Newton meter square per coulomb square. So here, for example, in a crystal, this is one of the example in the sodium atom here. In the crystal of the salt, an atom of the sodium transfers the electron to the chlorine formed in ionic bond. You know that in the ionic bond NaCl, the electron is transferred to the chlorine. So as a resultant here, the Q1 electronic charge is 1.6 into 10 raised to power minus 19 and Q2 is minus 1.6 into 10 raised to power minus 19. Because here in the sodium, Na is positive and chlorine Cl is negative. So this is positive, this is negative. This is positive, which is equal to 1 electronic charge positive. This is negative, which is equal to 1 electronic charge negative. So therefore, Q1 is equal to 1 electronic charge whose magnitude is always 1.6 into 10 raised to power minus 19. And Q2 whose magnitude is minus 1.6 into 10 raised to power minus 19. So these two charges are separated by a distance of 282 into 10 raised to power minus 12 meter. This is the distance between the Na and Cl in the crystal. So this is in the angstrom in general. So if we substitute these values in the Coulombs law, you will get the resultant force between Na and Cl is equal to 2.89 into 10 raised to power minus 9 Newton. So this is the way how to calculate the force between the two charges in the material, because Na is one of the atoms, Cl is one of the atom. When they combine together to form a molecule NaCl. Okay? So here again, This Coulomb force is due to the many charges. So now if instead of a single charge, if we have so many charges, for example, this is the Q1 charges, this is Q2, Q3, Q4 and Qn up to Qn. It means we have an n number of charges. On the same way, if we calculate how much force is exerted on the Q1 charge here, on this Q1 charge here, we can say that the Q2 is exerting force on the Q1, Q3 is exerting force on the Q1, Q4 is exerting force on the Q1, up to Qn exerting force on the Q1. So F1n is the force on the charge 1 due to charge n. F14 is the force on the charge 1 due to the fourth charge. F13 is the force on the charge 1 due to the charge 3, and so on. So the total force is the sum of the forces due to the all charges, which is equal to F is equal to F12 plus F13 plus F14 up to F1n. It means this shows that the force is exerting on a charge 1 due to the all other charges. So the force is the form of the summation. This summation is the vector summation. It means if the force is making certain angle, its angle can be resolved into two components, and we have discussed in the class that this force has a two components. One is the horizontal components, which is to be multiplied with the cos of angle theta, and other is the vertical component of the force, which is to be multiplied with the sine of angle theta. So here F12 is the force on charge Q1 exerted by the charge Q2 is equal to this, which is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R12 square into this unit vector. This unit vector is indicating the direction of the force, because this force is a vector quantity which has a certain magnitude and direction. Similarly, F13 is the force on the charge 1 due to charge 3, and so on. This is written here. Similarly, if we add up all the forces, the total force is the force due to charge Q2, is force due to charge Q3, is force due to the charge Q4, up to the force due to the charge Qn. So this summation notation is indicating the total force on the charge Q1 due to the all charges. So generally, the force is a vector quantity. So now the second thing is, what is the quantization of the force? Force की quantization क्या होती है? Simply, you all know that the total charge Q is equal to the number of electronic charges, and this E, which is the electronic charge, is equal to 1.6 into 10 raised power minus 19 Coulomb. So the total amount of charge is an integral multiple of the charge, and this phenomena is known as a quantization of the charges. The charges must be quantized in nature. If we look into the quarks has a fractional value of the charges, which is equal to this. For example, some quarks has a value which is equal to 2 upon 3 of E minus 1 upon 3 of E. This negative charge and positive charge is because of its nature. Here, if we say that proton is a positive charge, 1 of E. But you know that the proton and neutron, they are not fundamental particles, they are made of quarks. For example, the proton is made of 3 quarks, 2 up, 1 down. And neutron is made of again 3 quarks, 2 down, 1 up. So here, the charge of the quark is equal to 2 upon 3e minus 1 upon 3. If you add up 2 upon 3 plus 2 upon 3 minus 1 upon 3, again the total will be equal to 1 of E. So the proton will be charged of equal to 1, because 2 upon 3, 1 up quark, the second 2 upon 3, 1 up quark, and the third minus 1 upon 3, this is the down quark. If you add up all these 3, the resultant is equal to 1, and this 1 gives you the charge of the proton. If you look into the neutron is equal to 1 up, 2 down. 1 up means 2 upon 3, 2 down means minus 1 upon 3, minus 1 upon 3. This resultant gives you 0. Therefore, the neutrons are known as the neutral particle. So this is known as the quantization of the charges. If we look here, 2 upon 3e plus 2 upon 3e minus 1 upon 3e. This is the total charge of the proton. So 2e plus 2e minus e divided by 3, 3e upon 3e is equal to e. This e is the charge of the proton, which we call it as a positive e, which is the charge of the proton. Similarly, in the neutrality of the neutron, here two up, two down quarks. The charge of one down quark is minus 1 upon 3e. The second down quark is minus 1 upon 3. One up quark is charge is 2 upon 3e. So if we add up all these charges using LCM, it is resultant is 0. 0 means it is the again neutral. So there is no net charge on the neutron. So this is known as the quantization of the charge. You know that the charge can be conserved. It means this is known as a conservation of the charge. It means the positive charge and negative charge can combine together to form a neutral particle. For example, if we combine electron and proton together, it can form a neutral. If we combine electron and positron, positron is the antiparticle of the electron. Because you know that in the particle physics, every particle has its antiparticle. So here, one of the example of the conservation of the charge is the pair production. What is the pair production? In the pair production, the high energy gamma ray, this is the gamma ray. This gamma ray can be break into two particles, and one of the particle is electron and other particle is positron. So this neutral particle gamma ray, according to the Planck's quantum theory, the gamma ray, which is the electromagnetic nature, has a particle nature. So this gamma ray is in the particle nature, which is the neutral particle, is divided when it disintegrates, when it breaks, is into the two particle, one of the electron and other of the positron. So now here one of the condition that every gamma ray is not break into the electron and positron. There is a certain condition. The condition is that the gamma ray has a minimum energy is equal to 1.02 mega electron volt. If its energy is equal to 1.02 mega electron volt or greater than that value, then it may be possible the pair production will happen. Otherwise, this gamma ray will not break into the electron and positron. Similarly, pair annihilation. This electron and positron can combine together again in the form of the gamma ray, again in the form of the photon. So this is known as a conservation of the charges. The charges can be conserved from positive to negative and etc. So it means this negative charge can combine with the positive charge to form a neutrality, which we call it as a gamma ray. Here again, this electron is combined with the positron, is converted into two gamma rays. This is one. The other is the pion or meson decay. Here this pi is one of the particle, which is the pi 0. This particle can be decayed into two gamma rays. This is the neutron. The neutron can be decayed into proton and electron. This electron is a high energy electron, which we call it as a beta particle. This reaction is happening in the nuclear by the emission of beta decay. You know that there are certain radioactive elements in which the alpha, beta and gamma radiations are emitted out from the nucleus. We call that element is the radioactive element. So now in the radioactive element, if we say that this is the radioactive element and which emit out the beta particle. Now question is that how the beta particle, which is actually the negative particle, is emitted out from the nucleus. Because we know that there is no any electron or negative charge particle inside the nucleus. Inside the nucleus only we have a neutrons and a proton. Proton is a positive and neutron is the neutral particle. Then how the electron or neutral particle, how the electron is coming out from the, how the electron is coming out from the, how the electron is coming out from the nucleus. Here, in this reaction, the neutral particle, which is the neutron, is break into the proton and electron. So this proton remains in the nucleus and electron is coming out from the nucleus in the form of the beta particle. And other particle is emitted out from the nucleus, and which we call it as a neutrino. So now here, what is the electric field? You know that the electric field is one of the property of the charge, which is known as the electric field property. The electric field is defined as the space or region around which the influence of the electric charge can be felt, and that region is known as electric field region. So electric field intensity is defined as the force per unit charge. This force per unit charge is known as the electric field. If we say that the force is the electrostatic force on the test charge, this Q naught is the test charge. If we say that the magnitude of this test charge is very, very small, then it will not affect the force of the other charge whose electric field intensity is to be measured. Here, as you know that this electric field intensity is similar as that of the gravitational field. According to the gravitational field, the force is equal to mg. The force is equal to mass into gravity. So the gravity is equal to force upon g. So the same way electric field is equal to force upon Q naught. So again, if we can calculate the electric field of any droplet, this is one of the problem, which is the example. For example, in the Millikan's oil experiment, the radius of the Millikan's oil drop is equal to 1.64 micrometer. अब मिलिकन ऑयल ड्रॉप जो है एक एक्सपेरिमेंट किया गया था जिसमें ऑयल के ड्रॉपलेट को चार्ज किया गया था और उसकी चार्ज मालूम की गई थी कि हाउ मच चार्ज इज इंड्यूस्ड ऑन दिस ऑयल ड्रॉप. It means when you fire a radioactive radiations on the oil, it ionizes it. As a resultant, the droplet becomes a charged droplet. It means the charge is collected on the droplet. So we say that the radius of the droplet is equal to 1.64 micrometer and the density of the droplet is equal to 0.851 gram per centimeter is balanced when the electric field, which is equal to 1.92 to 10 raised power 5 Newton per Coulomb is applied. Find the charge on the droplet. We have to find the charge on the droplet. अब यहाँ पे अगर आप ये देखें कि इस पे दो फोर्सेस लग रहे हैं. एक फोर्स जो है ड्रॉप की वेट है जो डाउनवर्ड है, दूसरा फोर्स जो है वो इलेक्ट्रिक फील्ड है जो अपवर्ड है. अब अगर ये दोनों फोर्सेस बैलेंस हो जाएंगे तो जो ड्रॉपलेट है वो बीच में एयर में स्टैटिक हो जाएगा. फॉर एग्जांपल लेट्स से ये दो फोर्सेस हैं, ठीक है, ये दीज आर द टू फोर्स, दो प्लेट्स हैं, ठीक है, या यहाँ पे देखें दो प्लेट्स हैं. अगर इन दो प्लेट्स के दरमियान किसी ड्रॉपलेट को आप सस्पेंड करेंगे तो हम कहेंगे कि ड्रॉपलेट को नीचे गिरना चाहिए क्योंकि उसकी वेट है विच इज इक्वल टू mg. लेकिन यहाँ अगर ऊपर इलेक्ट्रिक फील्ड है तो वो ड्रॉपलेट ऊपर जाएगा इलेक्ट्रिक फील्ड की वजह से. अगर दोनों फोर्सेस बराबर होंगे, if the electric force which is in the upward direction is balanced by its weight of the droplet, then the droplet will be stationary there. So here we say that this electric force, which is equal to Q into E, is equal to the weight of the object, which is equal to force due to its weight. So QE is equal to mg. So Q is equal to, using cross product, is equal to mg upon E. So Qm is equal to rho into V. Because you know that the density is given. From density, the mass is equal to density rho into volume. Into G is this upon E. So if you substitute all these values, you will get the value of the Q, which is equal to 5 of the electronic charges. It means this dot plate occupies the 5 electrons from the nuclear ionization. So now, in the same way as we discussed that the force is the sum of all forces. So here again, the total electric field is due to the field due to the all charges. If instead of a single charge, if we have so many charges like that, if we have a charge Q1, Q2, Q3 up to Qn charges, then the total field will be equal to the field due to the all charges. E1 will be the field due to the charge 1, E2 will be the field due to the charge 2, E3 will be the field due to the charge 3, and so on. So here, this E1 is the electric field intensity due to the point charge Q1, which is equal to 1 upon 4 pi epsilon naught Q1 upon R1 square. Here, the electric field E2 will be the field due to the point charge Q2, which is equal to 1 upon 4 pi epsilon naught. This is field due to Q3, which is equal to Q2 upon R2 square. Similarly, this is E3, which is equal to 1 upon 4 pi epsilon naught Q3 upon R3 square. So as general, if we have a n number of charges, the total field intensity E will be equal to the field due to charge E1 plus field charge E2 plus field due to the charge E3 and so on. So here the total field is equal to 1 upon 4 pi epsilon naught. This is field due to the charge 1. This is field due to the charge 2. This is field due to the charge 3. And this is field due to the charge. This is field due to the charge Qn. So we add up all these charges to get the total field due to the all charges. Again, what is the field due to the dipole? Before starting this field, we have to discuss something here. So I have stopped sharing. So can you hear me? आवाज अच्छे तो पुत्र?
Yes, sir, आवाज अच्छे तो.
अच्छा.